Okay, so as I was saying, we have been looking at acceleration due to circular motion. So if we were to draw acceleration on this diagram, it is perpendicular to the velocity. So go at the end of your velocity vector on the circle, and it's perpendicular, and it goes into the center. I drew mine a little too far in there. Goes to it's center seeking, and here too. So this is our AC acceleration that's due to centripetal force. So if the centripetal acceleration is directed to the center of the circle, so must the force be. We've already kind of talked about that a little bit. So as we mentioned before, the center seeking force is centripetal. Centripetal force is any name given to any force that causes an object to move in a circle and pulls the object toward the center. It can be supplied through a string with an object whirling around, just like you guys did before. Frictional force when a car goes around, like is turning, but yeah, on a highway, you'll see. I'll get to another example. It can be gravitational force when the moon circles the Earth. It can be electric force when an electron orbits a proton. Basically, it's just anything in a circle. Okay? Doesn't matter if it's a tiny electron or a big car. It's all centripetal force. So how do we actually measure centripetal force? Well, now let's think about it too. When we had our thing from yesterday, we need to think about this as a horizontal circle. Okay? It's on a horizontal plane. Video. Horizontal circle, okay? If it was a vertical circle, it would be like this, okay? Going up and down so that it's being pulled by gravity, right? If it was better, you know what I'm saying? It would be going like this. Horizontal, it's just staying on the same horizontal plane, okay? So right now, all we're talking about is horizontal circles. Tomorrow is vertical circles. So anyways, so the force, the centripetal force, we don't look at gravity, okay? We're not looking at gravity because we're assuming it's just staying on a horizontal plane. Gravity is a factor, but we're not going to really include it in our math. So, centripetal acceleration can be derived from Newton's second law of motion. So we know, let's say F net is equal to m times a. So if we're solving, so then I will say, if I'm solving for a, it's a is equal to F net over m. Okay, so now I'm going to apply this to my centripetal motion. So a is going to be a subscript c is equal to Fc over m. So, and I set Fc to F net because Fc is the sum of all the center seeking forces. So now, we know from yesterday, or the day before, that AC is equal to V squared over R, or AC is equal to 4 pi squared times by R divided by T squared. So I'm going to substitute that in. I'm going to actually go back to just Fc is equal to m times AC. So now I can take these and substitute them into AC and to make two new formulas. So Fc is equal to m times by v squared over r. Or I could substitute in this formula into AC. So I could have FC is equal to M times by 4 pi squared R over T squared. Now take out your formula sheet. Okay, so are these on your data sheet? Okay, these are not on the data sheet, so that's kind of a big deal. So not on data sheet. So you need to know how to make these formulas. So you know, like these formulas are on your data sheet, these AC ones. You don't have to memorize those. And you know your F net equals M times A. So you just need to substitute in for AC. So just be aware that that's not on your formula sheet, but you have the tools on your formula sheet in order to do it. Okay?